Can you listen my sound? Hello. Am I
Yes,
audible?
sir.
Okay. There was some problem. I hope you can see this PPT. Can you confirm?
Yes, sir.
Is it fine? Hello.
Yes, sir.
Yes, sir.
Okay. So continuation with the last derivation. We will take one example how to exactly train this network. So these two equations are our importance. Say this 1 and 2. So equation 1 will be used here for all the weights, that is to update W matrix, and equation 2 will be used here to update V matrix. Now exactly how it is done, that we will see today. So this is the error back propagation algorithm. What we do now is, as a first step, we start randomly initializing the two important matrices, that is V and W. Since we don't know solution, we do assume these two matrices. Now how do I assume this? Now before I do anything, I must know how many nodes are there in hidden layer and how many nodes are there in output layer, and then how many nodes in the input layer. Now there is a fix, you can say, thing which tells you how to find out nodes in the output side. The output side nodes depends on number of classes we want to learn. Suppose I want to learn 5 classes, so the number of nodes at the output side will be 5. So this will be O1 to O5. Then the simple thing for input side, the input is number of nodes equal to dimension of feature vector. Dimension of feature vector. Remember that I have not shown here, but there will be actually one extra hidden node that if you are a programmer, that you will take care of. You will add one extra node. Suppose this is capital I number of nodes in the input side, then there will be I plus 1th node while you write a program. That will be xi1 plus xi plus 1, which is again given to everybody. Here input is always fixed to 1. So this is the augmented vector. Okay, since I need to accommodate, say for example y equal to mx plus c, so this plus c is accommodated by adding this constant. So this extra 1 is to accommodate that C. So the weight associated, or if I write in terms of weight, actually I should write say W1 X1 plus and so on up to Wn Xn, and there will be extra weight Wn plus 1. So this is that C in y equal to mx plus C. So, so this is the implementation of a neuron, and then to accommodate this Wn plus 1, I need to have one terminal here. Okay, so this will be say W in this case 1 and I plus 1 terminal. So this weight is important. So don't forget this, that there will be one hidden node for each layer, and it is connected to all the neurons in the subsequent layers. So there will be one more hidden layer here, hidden not layer, hidden unit here, and that is connected to everybody. Okay, and this has fixed input plus 1, and the corresponding weights will be updated as per the rule. Say you are updating for this, then you will use this formula, and for this you will use this formula. So there will be extra node for each layer that you should keep in mind. So I'm not showing here, but it is there. Or you can add here for your reference. It is I plus 1, and this is connected to 1, so that you can add here and then you can connect accordingly. Okay, so there will be one more node here that is connected to everybody. Input to this will be equal to 1. Now, so I hope you got the idea of input layer, output layer. So number of nodes in the input side equal to number of features that you are using for your problem. So there are 100 features, then there are 100 input nodes. If there are say 20 classes, then output side will have 20 output nodes. Now question remains, how many hidden units? Okay, so how many hidden units? So as such, there is no rule or no guideline for this, but with the help of experience, we can find out how many hidden units I need. However, as a general rule, you can remember uh, to begin with, you can suppose you have 10 nodes in the input side, then you may go 2n, that is 20 nodes for hidden sides. It may be big for many problems, but this is a general thing. You may require in general 20 to 25 nodes. Okay. The idea is this hidden node, or sorry, this hidden layer will do the mapping of all the samples from X domain to some intermediate Y domain, that they will be linearly separable. So this mapping happens with the help of increasing the dimensions. Okay, so when you do increase the dimensions of input, then there is quite a bit of chance that they will get linearly separated. So that's why I said that you go with 2n. If you have 5 nodes here, then go with 10 here. And output side will be number of classes. So if you are learning 7 classes, put 7 nodes here. So this will be your architecture. Now this will define the dimension of V matrix and W matrix. Okay, say suppose I have 5 here and 7 say 10 nodes here, and I'm learning suppose 5 classes, or let us take intentionally some other number. Suppose I'm learning uh, 9 classes. So this 5, that is, you have now 10 nodes here. So 10 nodes means you will have one row for each neuron. So you have this 10 lines or 10 rows for 10 neurons. Okay, and then you have now 5 columns here. So the matrix V, so if you consider the extra node, then you have 6 actually. Okay, so you have 6. So 5 plus 1 is 6. So the dimension of V matrix is 10 by 6. Now this is W matrix here. So W matrix here will have, say here I have 9 neurons. So there are 9 rows. Okay. Remember, number of rows equal to number of neurons, and number of columns is equal to dimension of input. So dimension of input here is 10, and then 1 extra for next layer. So it will be 11 columns. So W matrix is of size 9 by 11. So once this is done, say V is 10 by 6 and W is 9 by 11. The activation function is the next thing that you must decide before you start training. So activation function is generally used as bipolar sigmoidal or unipolar polar sigmoidal, that is tanh or your logistic uh, function. And once you decide these things, one more thing left is learning constant. So you can choose a small learning constant like 0.1, and then you can start training. Okay, so what things you will require? You will require to decide input nodes that I said equal to dimension of input vector. Then you require to decide hidden units. So in general you take twice of this dimension, so twice of this, and then output layer nodes, that is equal to number of classes. Okay, so these are the 3 things you must start with. Next one is learning constant. You choose a small, maybe 0.5 like this learning constant, and for every layer you can define own activation function, but in general it is done with bipolar sigmoidal or tanh function. Okay, so these are 5 things you must assume before you start training. So once you decide that, you then randomly assume initial weights for W and V matrix. So this will be your first step. The second step is to compute the output of the layers. So let me clear this. So you have decided randomly value of V here. You have decided randomly value of W here. Then you will apply first pattern X1 and it will have its desired vector D1. So this input is applied. It will be multiplied with V. You will get net values for each neuron and then you will pass those net values through the activation functions here. That will give you Y values for each hidden unit and that will be forming hidden output vector. And then it is passed on to next layer, that is output layer. It will be multiplied with W matrix. This will be producing net values for all output layers neuron, and activation function is used later on, and this net value is passed through those activation functions to give you final output. This final output is compared with this desired vector and error is computed. Okay, so you know error is d minus o half square summed over all the units. Okay, so this error is computed and then the actual training using backpropagation starts. So the step number 2 is to compute this output. So this y equal to some thresholding function vz indicates that it is computing output of hidden layer, and then this y is used to compute output of final layer. Now once you do that, you compute error. This error is then used to calculate delta, that is error signal for output layer, and delta y, that is error signal for hidden layer. So you can note that this is a delta 0, that is out, delta O, that is error signal for output layer, and there is delta Y, that is error signal for hidden unit or hidden layer. Then the weights are adjusted, so W is changed and then V is changed or V is updated, and then if there are more patterns then they are taken. So once all the patterns are over, then it will be checked whether error, current error is acceptable or not. If not, then retraining starts. So that's how this will work. If error is less than what we expect, then we will stop. Now we will take a small example. This is a hand-run example so that you will come to know all the steps. Say I have here input vector x. So this should, I think, x small x. Anyway, so This is the input vector x capital X1, which has the corresponding desired response. And there is another training example and its desired response. The network is with two input units for, sorry, two hidden units for uh, this step and 2 units for output. Input is single actually, and this is the fixed node connected to -1. So you can connect either +1 or -1. So in this example, we are connecting it to -1. So actual input is single dimension. Because of this -1, it has become 2 dimension. So this is a fixed node. You can see another fixed node here connected to -1, and it is given to the two output neurons. So this is the structure. So let us see that we have randomly assumed, say, V matrix and W matrix like this. So V matrix consists of two rows corresponding to two neurons here. Okay, there are two neurons in the hidden layer. So this is the weight of neuron 1, this is weight of neuron 2. So this will be 1 here, -1 here, and this will be 1 and 2 here. Similarly, this is weight for neuron number 1 in the output layer. This is weight for neuron number 2. So this will be 1, 1, 1 here, and 2 -1, -1 here. Okay, so this is how we randomly assume V and W. Now next step is to find out the output for given input. So this is our first input, and that is the corresponding desired response. So the weight updation formula is used for hidden layer is this one, and this change in weight will be used here. Now let us find out the output of layer 1, that is the hidden layer. So net 1 is V into X1. So this is my V and this is V X1. So V into X1 will directly give you the net values for two neurons in the hidden layer. Now these two net values we will pass through tanh function so that you will get output directly for hidden layer. So this 0.96 and minus 0.76, 0.96 and minus 0.76, these are outputs for hidden units. Now this hidden unit output is now suffixed with -1, that is extra node that we have created, and then we will multiply with W. So this will give you the net values for output neurons. So the net value for output neurons is this, and the output will be calculated when you pass these net values through tanh function. Remember, we are assuming tanh function as activation function for neurons. So the output, final output is -0.66 and 0.99. So here it is 0.66 and 0.99. But what is expected here? It is -1 and +1. So I want here +1 and -1, but what I am obtaining is this value. Okay, so this new network is not trained for X1. So I need to change the weights. So error is D minus O. So this is the desired vector and this is the output vector. So if I do D minus O, this will be D minus O. And then I want to change the weight for output layer. So we start from, remember, we start changing weights from output layer. Then we will go to hidden layer. So the formula is here. Out of that, these two terms is, these two terms, multiplication of these two terms is called as delta OK, as we have seen in last class. So this we will remember for our further calculation. So this is required for updation of hidden layer. So this delta OK, that is signal for error signal for output layer, there are two deltas, that is delta O1 and delta O2. Since there are two neurons in the output side, if there are 5 neurons, then this will be delta O3, delta O4, delta O5. So this will be called as delta O vector. Okay. So now here we have only two. So I'm calculating delta O1 and delta O2 equal to. So the same formula, this one I am using here. So desired response of first neuron minus desired output of first neuron. So that is 0.44. So I am writing here. So this is D minus O into F dash of net. So F dash of net for tan H, if you remember, is 1 minus O square. So F dash of tan H function is 1 minus its actual value. So if O is equal to tan H, then O dash is 1 minus O square. So this 1 minus O square is written over here. So output is minus 0.66, then you square it and subtract from 1. So this complete multiplication will give you delta O1. Similarly, the error is 0.01, which is kept here for second neuron, multiplied by its f dash. So the derivative of output is 1 minus 0.99 square. So that is written here. So this is delta vector or delta O vector for output side. This I am going to remember because it is required to calculate hidden weight updation. Now we will update the output weight. So this is the old vector we have assumed plus the learning constant. Suppose I take 0.1 into delta O vector multiplied by input, that is y. So it is the outer product of two vectors. So this will give you a matrix. This will give you a matrix which, let me clear this thing. So here remember W new is equal to W old plus delta W. So this delta W will come from this thing. Okay. Now what has happened is this is calculated. Say this delta OK for each neuron is already calculated, that we have to multiply with the input vector for that particular layer. Okay. And this we have to do for all the neurons. So it will be again a matrix added with the old matrix, and it will give you a new matrix. Now a shortcut is, or you can say, you can use the commands in the packages which will give you directly this, and it will give you this required product of all deltas with all the weights, all the inputs immediately. So this will be the step. So this is your delta O vector multiplied by input. Input means input of output layer. So this is the output of previous layer and suffixed with -1. So that will be your input of output layer. So this will give you a matrix of same size so that you can add immediately. And this is your W new. So this is updated weight of output layer. Now we need to update hidden layer weights. So hidden layer weights you can update using this formula: delta Yj is equal to summation k equal to 1 to capital K delta OK into Wkj into f dash of net j. So this is delta Yj. So this delta Yj, you can see this delta is again multiplied by its input. Okay, so this is same procedure repeated for every layer. So in earlier case it was its input. Now for hidden layer it has its input multiplied by its delta signal. Okay, so let us see how to do this. So delta y1 and delta y2, these are two error signals for hidden side. Okay, so we were done with delta O, now we are doing with delta y. So there are two delta y, delta y1 and delta y2 here. Earlier we have delta O1 and delta say O2. Now delta y1 computation requires delta O signal. Okay, so this is the computation of delta y1, the first one. So we have two classes. So the summation will run for k small k equal to 1 to capital K delta OK into wk1 into f dash of that neuron, f dash of net j. Similarly, we have delta y2 computation. So this is delta y2 computation. Here we are doing it for this neuron. So this k again will run from k equal to 1 to 2. Now here you can see there is a change, wk2. I am dealing with now wk2 into its f dash. Okay. Now suppose I draw here. Now see what is happening here. To compute say delta y1, what I am doing, I am taking wk1, means where is wk1? K is from 1 to 2. So this will be, suppose k equal to 1, this will be delta O1 into W11 plus delta O2 into W21. So where is this? So delta O1 multiplied by W11. So these two are getting multiplied, added with delta O2. So this delta O2 into W21. So where is W21? So this is W21. So weights connected to this hidden unit and connected to next layer. So these two weights, they are getting multiplied by the error signal for these units, that is output units. So error here is multiplied by its importance. Error here gets multiplied by its importance. So these two added together is the error signal for this neuron. Now suppose I want to do it for here, second neuron, you will see that I will multiply this delta O1 with weight here. What is weight here? It is W12 and then this weight here. So this delta O2 will get multiplied with delta, sorry, weight W22. Okay. So what we have to do in general, we have to take, say for example, this node, if I want to calculate error signal for this, then you look forward from this node and see how many connections you have. You may have more connections like this. Then you see the weights of each connection and multiply it with the error signal for calculated for next layer. Okay. So addition of all this will result into this delta y. So okay, I hope this is clear. You can see here same thing happening. So if I expand this, this will be the expansion for the two things, and when I multiply, this will be the delta signal. Out of that, this will be delta y1 and this will be delta y2. So this is the error signal for hidden side, and this delta y will be used if there is one more layer after this, okay, or before this. Now we have to change weight of hidden side. So V new is equal to V old plus some learning constant into dy into x transpose. So this will immediately give you the matrix required for updation. So this in fact is change in, say, V matrix. This outer product will immediately give you this change in V matrix. So substitute here values. So this is our weight V and this is learning constant. This is our delta signal that we have calculated, and this is our input. Input is just 1 minus 1. So once you do this outer product, it will be a matrix. So this will be a matrix and multiplied with learning constant. So that will be equal to 0.9982 and so on. So this is my new V, and we have already calculated W new. So V new and W new, you will substitute now here. Okay, so this next input x2 will face these updated weights, not the initial guess. Okay, so every time the new input comes, it will face the updated weight. So this is the now V and W. Now we have to repeat this procedure for all the samples. So I just repeat this step. Randomly assume V and W initially. Then we take the X1 and we change, say, weight matrix to V1 and W1. Then we take X2, we change it W2 to up to Xn. We change the weights like this. Once everybody is over, that is all training samples are over, we calculate the overall error. If it is acceptable, then stop. Otherwise, you repeat the procedure. Now, when you repeat the procedure, this last updated weights you will carry forward. You will not randomly assume again from the beginning. This last updated weight you will take as the input for next iteration. So like that, you will repeat. So this is the way we update this multi-layer network. So if you have any doubt, you can ask. Otherwise, we will stop.
Sir, can you repeat once again from layer 2, just a summary, sort of?
Okay. This one, this slide, is this fine?
Sir, from Bell, okay. Uh, just steps, can you?
Which slide you want? Can you just give me hint?
Next. From Dell, okay, sir. Uh, can you calculate
You
the
can
input?
just tell me. I will stop on that slide. I'm just scrolling
Okay, sir. From,
all the
yeah.
steps. I'll explain this one.
Sir, Dell, okay. Previous slide before this.
Okay, anyway, so I just repeat what I said once again. So we started with, say, input x1, and then we calculated output of this network and compare with its desired response. So once I know the desired response and output, I can calculate delta for each neuron here. Okay, so this calculation will tell me how to update weights here. So this is nothing but delta signal. So this is delta O1 for this particular neuron, and this will be delta O2 used for second neuron. So this combining these two numbers will give you delta O vector. It's very simple, just collection of these two numbers will give you.
Sir, for this delta O vector, we are not multiplying with input then. Uh,
No, no.
like in
For
general,
delta,
delta rule,
we
we
only
will
we
do
have to
that.
take these two terms, right? When we want to update, we will multiply with input.
Okay.
So this delta signal will be used here. Okay, you can see here there is only delta OK used, not with Y. Okay, so that is coming from our derivation. Just I am repeating what our derivation is telling us. So this delta signal is required to compute delta Y1 here and delta Y2 here. Now how it is computed? Just 1 second. I will discard all these drawings. I just repeat. So this delta O1 and delta O2 is suppose calculated. Then I need to calculate delta Y1 and delta Y2. So delta Y1 and delta Y2 is computed using this. Okay, so this box is delta Y1 computation. Now what this box is telling you, so you can, instead of remembering formula, you can remember like this. So if I want to compute delta Y1 here, just look forward how many neurons are connected from this node onwards. Okay, suppose there is one more here, then there will be connection here also, and there will be its delta also. So the weight here is, suppose W11, this is number 1, and suppose this is number 2, then this will be W11, this will be W21, this will be W31. So what is fixed here is the second digit. Okay, so this is fixed because we are dealing with this node, and the first number indicates this neuron in the next layer. Okay, so this W11, W21, W31 is this connection. Now what we have to do, take this delta O1 multiply with W11. So delta O1 multiplied with W11 plus this delta O2 multiplied by its weight W21 plus, suppose there is delta O3 multiplied by W31. So once you add all this, this will be delta Y1. Okay. Now let us do it for second also if you want. Suppose I want to calculate this one, then these are already calculated. So what I have to do, I have to find out this weight. So this weight is W12 and this weight is W22. So delta O1 multiplied by this weight. So that will come here. So this, you can say this error signal is multiplied with this weight. So that will be giving, say, importance to this signal. If this weight is more, then importance to this error is more. Okay, importance of this error generated for this node is taken care more by this node, and this delta signal will get multiplied with weight associated with this connection, and that added here will give you delta y, and this delta y which is written here is multiplied with its input will give you change in weight here. Now suppose there is one more layer here. What you will do, you will use now this delta y to compute, suppose some delta p here, delta p1, delta p2, delta p3 and so on. What formula you will use to find out this delta? You will use, can you now tell me what formula you will use? you'll use same thing. Okay, you will use same thing. That means you will take this delta y1, you will multiply with its weight here, then you will take this delta y2, you will multiply with this weight, added together will give you this delta y. So like that you can proceed for so many layers. Okay, so once you compute delta for last layer, it will be propagated in reverse direction. That's why it is called as error back propagation. So error signal is in the form of delta. I hope this is clear now.
Yes, sir.
So let us stop now.